So you can access all of our information via our link tree, our social media. If you go ahead and scan this QR code, I think that's just about it. I am not Kelly Huff. I'm filling in for Kelly Huff, but my name is Jen, and this is Dan. So Veritech is a system solution provider. We provide MEP and control solutions for just about any type of vertical market. And together, we're shaping the future of HVAC. And part of that is our educational initiatives, which we're very proud of. And as a result, we've created a mission statement to empower the industry through education, which is evident not only in our webinar Wednesdays, which you're on, but also our newsletter and other educational initiatives. Next slide. So with that, this will be recorded, and that recording will be available on our website, veritechsolutions.com, via the training tab, so that you can use this as a resource for your future needs. Next slide. And again, we have other education initiatives along with not only just our webinar Wednesdays, but also our newsletter. So if you are not currently receiving that newsletter and you would like to, then feel free to reach out to Kelly Huff and she will get you signed up for that so you can receive that as well. Next slide. So these are our upcoming webinar Wednesday topics. As you can see, we have Psychrometrics Part 1, and then we will be having outside air systems, and then Psychrometrics Deconstructed Part 2, and then another one in November. We will be ending for the year. After that, we will not pick back up until February of the next year. So with that said, let's go ahead and introduce Dan, who will be presenting today. He is a 40-year veteran. He has lots of experience in this industry, so you are in great hands. Next slide. He has also been an active member of ASHRAE starting in 2009. And some of the testaments to that commitment that he has to the organization is that he is a voting member on both ASHRAE Standard 200-2015, which is methods for testing chilled beams, as well as ASHRAE TC 1.7P, which is ongoing commissioning committee. And another thing to note, which we're very proud to announce, that as of July, Dan is now a distinguished lecturer for ASHRAE. So something to be very proud of. Congratulations, Dan. We're lucky to have you on the team. And outside of ASHRAE, Dan has also been a part of 7 publications in ES Magazine, authoring and co-authoring. And with that, if you have any PH credits that you are wanting to receive on this, make sure that the name that you have on there is something that we can utilize for that. Yeah, that is it. Take it away, Dan.
Jen, thank you very much, and thank all of you for joining us today for another webinar Wednesday. We appreciate your time commitment, and hopefully you'll be able to pull some good information from this session. My name is Dan Hani, Director of High Performance HVAC Solutions. So let's begin with a fundamental topic, perhaps the very foundation of what HVAC is, and that's psychrometrics. So today we're going to offer some context, first of all, for psychrometrics as to why we need, what it is and why we need to apply it. But before we do that, we want to evaluate how changes in the industry are going to demand that we look perhaps more closely at psychrometrics than we have in the past, and I say that for various reasons. We're going to look at the White House indoor air quality initiatives that were initiated in 2022. And then we're going to look at the Clean Air in Buildings website from the White House and what the White House is recommending in federal agencies to create cleaner air in buildings. And then we're going to look at heat transfer. We're going to look at properties of heat transfer and the various terms and definitions applied. And then just quickly, a review of the history of the psychrometric chart. Then, of course, we'll delve into psychrometrics and the properties of air. its history and purpose, terms and definitions, and then we're going to throw a hand grenade onto the chart and blow it up and deconstruct it and rebuild it so we can make, at least in my mind, have a better understanding, clear understanding of what all the lines mean and how do we apply them to evaluate the properties of air. We'll look at a quick application of the chart to resolve an issue of condensation occurring in the building, and then we'll review the presentation. So let's begin. The White House Indoor Air Quality Initiatives. On October 11th, 2022, the White House launched, to my understanding, the first IAQ summit. COVID-19 really precipitated a lot of federal initiatives that began to evaluate, is the air quality in our buildings adequate to maintain personal health and to prevent the spread of contagious infections? And so it created this summit in anticipation of what could possibly occur with COVID-19 in 2022. And it made this statement that the improved indoor air quality is fundamental in mitigating the spread of COVID-19 and any other aerosolized pathogens. And consequently, it initiated its Clean Air in Buildings Challenge to create better indoor air quality, to improve human health, and to reduce the risk of infection. Well, there's a reason for that, because indoor air quality significantly impacts human health. It goes on to state within the Clean Air in Buildings Challenge that the quality of cleanliness of the air we breathe every day has a significant impact on our health and well-being, something that we should all be concerned about. Well, for any building owner that signs up for the Clean Air in Buildings Challenge, they commit to they make 4 commitments. And I want to draw your attention to commitment 2, and that is to optimize fresh air ventilation, bring as much clean outdoor air into the environment as possible. Well, that demands that we really make sure we understand the properties of air and what that means with regard to building load and how we can assign a value to that applying psychrometrics. The CDC during the pandemic also recommended to create healthier buildings and reduce the risk of infection, to increase the outside air ventilation rates to buildings, if not eliminate completely HVAC air recirculation. Well, that was rather interesting to come out with that pronouncement. The EPA was arguing this similarly, and that inadequate ventilation can increase indoor pollutant levels by not bringing in enough outdoor air to dilute emissions from indoor sources. So increasing outdoor air ventilation rates to buildings was accepted by the CDC and the EPA for creating healthier environments. But it begs the question, certainly in various geographical areas in our country, as to whether or not we want to bring in more outdoor air, considering the contaminants and pollutants in the outdoor air. A very legitimate concern. Well, I was surprised when I learned this statistic from the EPA website, that it has a statement that indoor levels of pollutants may be 2 to 5 times and occasionally more than 100 times higher than outdoor air levels. In fact, there's a very interesting development with regard to outdoor air realizations. Dr. Joseph Allen from Harvard University has published a very compelling book called Healthy Buildings. He actually has a calculation to demonstrate that because we spend 90% of our time indoors, we breathe more outdoor air indoors during the day than we do when we are outdoors. We spend 90% of our lives indoor versus 10% of our lives outdoors. So regardless, you're breathing outdoor air anyway. So consequently, the chances are that the contaminants outdoors are less than indoors, because indoors you have not only the outdoor pollutants, but also the indoor off-gassing, both of occupants and various other chemicals that are used in the making of materials that go into buildings. ASHRAE is now evaluating another indoor air quality concern, and that's CO2 concentrations. there's some interesting discussions going on about, is the current requirement of 700 parts per million greater, no more than 700 parts per million greater than the outdoor CO2 concentrations adequate, considering our elevating of CO2 concentrations outdoors? And so the only way to reduce CO2 buildup in buildings, which on a national average appear to be at about 1,500 parts per million, ASHRAE is looking at, well, maybe we need to make a firm 1,000 parts per million a max CO2 level indoors. And there are even some arguments saying, no, maybe between 600 to 800. Well, the only way to control CO2 concentrations indoors is by bringing more outdoor air into a building. And so just be aware of that. Another national development, of course, is the industry trend moving towards decarbonization. And ASHRAE has very much embraced a direction for the built environment to adopt decarbonization design strategies to reduce greenhouse gas emissions. Well, ASHRAE Standard 90.1 is very aggressively attempting to reduce as much greenhouse gas emissions generated by the built environment, both through operation of MEP systems, but also with embedded carbon. And the Department of Energy issued on March 6, 2028, the determination that ASHRAE Standard 90.1 2022 will be the new improved energy efficiency standard for commercial buildings. Why? Well, because by their calculations, they've come to the determination that another 9.8% energy efficiency will occur by the adoption of the 2022 standard over and above the 2019 standard. So the industry for the built environment is moving towards more efficient buildings. So the good news is that as buildings become more efficient and sensible heat gain in a building, and we'll discuss what sensible heat actually is shortly, that the actual thermal energy gain in the building is being reduced because our perimeter walls are becoming better insulated, our glazing is more effective in reducing solar radiant loads, our lighting is moving from incandescent to LED. There are a number of factors. Well, as your sensible heat gain diminishes, your airflow requirements to meet summer design conditions also is reduced. However, it doesn't address the issue of humidity. What about humidity? Humidity is humidity. We still have the same amount of humidity levels, and consequently, we need to understand how to handle humidity as our airflow requirements are being reduced to meet our sensible heat gain in buildings. And it begs the question that we're seeing here in Phoenix, Arizona, whether or not 55 degrees off of a coil to maintain a building at 75 degrees, 50% RH during our Phoenix monsoon can be attained with a 1.8 degree dew point depression from the airflow supplied to the built environment if our airflow rates are decreasing. So in order to make that assessment, we better understand the properties of air very closely to make sure our MEP systems are adequately handling the humidity in a building to overcome the reduction in airflows that would were otherwise applied in less efficient buildings. So let's first of all, before we examine psychrometrics, make sure we have a common understanding of heat transfer. What are the properties, terms, and definitions of heat transfer? And then we're going to look at really a rather interesting snapshot of the history of the psychrometric chart. First of all, what is the purpose of a heating and ventilating system? Well, it is to generate an environment, to create an environment that provides thermal comfort for occupants and good indoor air quality to promote personal well-being, and now, since COVID-19, to reduce the risk of infections. Well, what is thermal comfort? Well, that's a very subjective term, and ASHRAE recognizes that. But in order to maintain thermal comfort, temperature has to be maintained within a given range. And normally we see 70 to 75, maybe 77, 78 in some of the newer high performance building solutions. We won't go into that. Well, in order to maintain temperatures in a building, you have to transfer energy. The energy gain in that building has to be deposited outdoors during our peak cooling conditions in order to maintain thermostats and temperature levels as a constant. So to do that, we have to transfer energy. So what is heat transfer? It is any or all of several types of phenomena that convey energy and entropy from one location to another. And it can be done in two ways. One is passively, allow the forces of physics, the forces of equilibrium, that to allow energy to transfer from a high energy state to a low energy state. It's going to happen due to the laws of physics, or it can happen artificially or mechanically. Well, today we're going to be talking about predominantly mechanical heat transfer. In order to do that, let's look at the terms, first of all, of energy, because that's the term that we're trying to move. What is energy? Energy in physics is the capacity for doing work, and it exists in different forms. There's potential energy, kinetic energy. We're going to discuss thermal energy. There's also chemical and nuclear, etc. All forms of energy are forces associated with motion. Energy is a force, and it is directly or indirectly the agent for motion, quantitative and qualitative change. In built environments, to have heat transfer, we need to use electrical energy to mechanically transfer thermal energy to and from buildings. So when we're trying to cool a building, the fundamental purpose of an HVAC system is to move energy from a building to outdoors. Specifically, the amount of energy gained within a certain period of time in order to maintain space temperature conditions. So we have to move that energy building up in a building to outdoors. In dehumidification, we also have to be aware of latent cooling, which is the reduction of the amount of water vapor within a building that generates humidity, that creates a humidity value, and we'll discuss that in greater detail shortly. In heating season, we actually add energy to the building because the heat energy buildup in the building is absorbed to the outdoors, to the colder environments due to passive heat transfer and the forces of equilibrium. Well, how much heat needs to be transferred? Well, we have to calculate that amount of heat that needs to be either removed from a building or added to a building. How do we do that? We apply psychrometrics. And the conventional way of moving energy in a building is using air as a heat transfer medium. Why do we use air as a heat transfer medium? Because it is a fluid and has mass. And because it has mass, it has the capacity to hold thermal energy. That's why we have diffusers populating ceilings to supply large amounts of air throughout a building to capture the heat energy gained within that building and return it to an air handler through a return air duct, where that energy is removed at an air handler cooling coil and in some fashion, either through a condenser or a chill water loop, deposited outdoors through a central plant. Air also, however, is a conveyor of water vapor because water vapor is a gas, and air samples contain various concentrations of water vapor or relative humidity. Well, air can also be used as a water vapor transfer medium so that we can absorb the water vapor or humidity increase in the space due to occupants, sinks, any other water source within a building, and take it to a cooling coil within an air handler where it can be removed. And then that drier air supplied back to the building so that the condition in the space, the air supplied to the space can absorb the additional continual humidity gain in that space. So HVAC systems and environmental control, an HVAC systems controls the amount of thermal energy and humidity in a building to maintain thermal comfort and to provide good indoor air quality. Well, I've referenced temperature a couple of times already. What is temperature? Temperature is a measured value at a thermostat assigned to thermal energy present in a sample of air. What is that thermal energy actually in a sample of air? Or what is temperature actually doing? Well, it's measuring the rate of molecular motion of a sample of air. And I couldn't get my head around that for years until I had to build a PowerPoint. And I said, Dan, it's about time you learned what this is. The amount of thermal energy in a sample of air determines the rate of molecular motion of the air molecules in the air. The greater the amount of energy, the faster the molecules move. The faster the molecules move, the more frequently they bombard the surface of the skin, creating a sensation of warmth. If you remove that thermal energy, the molecules slow down and the skin has a lower rate of impact from a molecular movement in the air, and consequently has a sense of cooling. So the higher the molecular energy within a sample of air, or kinetic energy, it results in a higher temperature read at a thermostat, and the amount of energy you actually feel is heat. Consequently, thermal energy is also known as sensible heat energy. It's the energy we feel. It's warm in here, it's hot in here, or whatever, due to the rate of molecular motion. What is humidity, and how do we measure humidity? Well, humidity, according to ASHRAE standard 55, is defined as the moisture content of the air. And we can either measure that moisture content relatively using relative humidity, a term that we reference daily in our weather reports, or we can evaluate it and measure it absolutely by looking at other factors such as dew point, specific humidity, and absolute humidity. And we're going to evaluate all these terms in greater detail shortly. But what's interesting is that humidity, of course, is water vapor, and water can exist in 3 states. What determines the state of water, whether it's a solid, liquid, or gas? It's the amount of energy present in that sample of water. So if you remove enough energy from water, water ceases to be a fluid and becomes a solid or ice. And if you add enough energy to a sample of water, it evaporates into a gas or water vapor. So consequently, humidity levels within a sample of air are determined by how much energy is present to that sample of air. Well, water vapor requires energy to be in a vapor state, and that energy is referenced as latent energy. You can't feel it as energy as you do heat or sensible heat energy, but it is present to keep water in a vapor state. So if you're in an environment that has high humidity, you feel dampness. There's a lot of latent energy that you don't feel as thermal energy or surface heat on the skin. You actually feel it as dampness in the air, but it is still an energy factor. And this is why I say that HVAC systems fundamentally are concerned with how much energy is moved from or to a building in order to maintain building conditions. HVAC and energy are just correlational. Let's look at the term thermodynamics, and let's start breaking down what the terms of air mean and how do we understand them to evaluate energy present in a sample of air. Well, thermodynamics is the study of the relationships between heat, work, temperature, and energy. Let's look at the term enthalpy, a term that is found on the psychrometric chart. The term enthalpy is the total energy in a sample of air. What is the total energy? Very simple. It's the amount of sensible energy plus the amount of latent energy in a sample of air. So in order to know how to maintain building set point conditions, we have to calculate and assess what type of equipment needs to be moved, the amount of energy necessary to maintain building conditions at comfortable levels. So in order to do that, we have to apply psychrometrics. the study of the thermodynamic properties of air vapor mixtures, partial pressures, and enthalpy. Just as a quick aside, what are psychrometrics? Well, actually the term is derived from two Greek terms. One is psychro, meaning cold, which really cold is the absence of heat by definition, and metron is a means of measurement. So those are the root words of the term psychrometrics. Well, the psychrometric chart had a more considerable history than I had anticipated when I began researching it. Actually, there was a wonderful article in the 2004 ASHRAE journal on the history of psychrometrics. In fact, it was the psychrometric chart celebrates its 100th anniversary, and I was surprised to learn that an understanding of the properties of air and the relationship between thermal energy and water vapor and barometric pressure and etc. can be assigned and tabled and measured. And we first, if my understanding is correctly, the first hygrometrical table was invented by James Glaisher in 1847. The properties of air that Mr. Glaisher was able to evaluate and assign was expanded upon by the American meteorologist William Ferrell in 1886. And that good work was actually taken even further by a Professor Charles Marvin in 1900. It was the German physicist Richard Mollier who actually helped to codify in a more easily interpretive chart called the Mollier diagrams in 1904 that illustrated the relationship between moist air and thermal energy. However, the father of the psychrometric chart as we know it today is one Willis Carrier, who applied the Mollier diagrams to try to determine a way to resolve the humidity issue for a project he was working on called Wilhelm's Lithographing and Publishing Company. And after that exercise and the amount of work that it took to run those calculations, Mr. Carrier decided that there's a better way to do this, and he came up with the psychrometric chart to simplify the task of air conditioning design. And it is that chart that we use today fundamentally to determine the properties of air and evaluate the amount of energy present in a sample of air. So let's look at psychrometrics and the properties of air. So again, in order to maintain building at set point conditions, we need to understand how much energy needs to be moved to or from a building to absorb or to add to a building, the amount of energy added or taken away during the cooling and heating seasons. So in cooling, we have to calculate, or one has to calculate the amount of total load added to a space through a period of time that needs to be removed to maintain constant conditions. So remember the terms that we spoke of earlier called sensible energy, the amount of energy present in a sample of air measured at a thermostat, and latent energy, the amount of energy necessary to keep water in a vapor state. So how do we determine that? Again, we apply psychrometrics. So before we begin using the psychrometric chart, we need to make sure that we have a common understanding of the terms used on the chart. There is dry bulb temperature. Dry bulb temperature is the temperature that measures the sensible energy within an environment at a thermostat. Sensible energy is the heat sensed by an occupant as heat. We need to understand what relative humidity is. Relative humidity is the moisture content in a sample of air as a percent of the total amount of moisture air can hold when fully saturated at 100%. Relative to what? Temperature. And this can be a challenge, using relative humidity as a measure for the amount of water content in a sample of air because it is dependent on temperature. And this explains why ASHRAE standard 62.1 has moved from relative humidity levels as minimum levels to maintain proper indoor air quality, and they've moved from relative humidity to dew point, which is an absolute measurement of water vapor in a sample of air that we'll review here presently. There's another term called wet bulb temperature. What is wet bulb temperature? It is the temperature measured by a sling psychrometer. What is a sling psychrometer? Well, in the old days, I think I qualify for that because I do remember sling psychrometers. A sling psychrometer is a device with a handle with a rotating arm that has two thermometers. One is a dry thermometer to measure dry bulb temperature within a space. The other is a bulb thermometer with a wet wick attached to it. And that psychrometer is slung around in a space to measure the rate of evaporation by how much the temperature is lowered on the wet bulb thermometer. And the more humidity in the air, the lower the evaporation rate and the lower the cooling of the wet bulb thermometer. The drier the air, the higher the evaporation rate, the more energy is absorbed from the air local to the wet bulb sensor, and the temperature decreases more. So the wet bulb temperature is the temperature read from a sling psychrometer that assesses the amount of water vapor in a sample of air through the evaporation rate of that wet wick. Dew point temperature is the temperature at which insufficient energy is present to maintain water vapor in a vapor state, and water vapor condenses to a water liquid. That is known as dew point. There is specific humidity, which is another absolute measure of water content in a sample of air. It is measured in grains of moisture per pound of air. Well, just to give you an idea, in a form of reference, there are 7,000 grains in 1 pound of water vapor. So this is an absolute measure, because if you actually use humidity ratios to measure water vapor content within a sample of air, it is not temperature dependent. You'll have the same amount of grains at an air sample that's at 75 degrees, and it might be raised to 100 degrees. Well, you still have the same amount of grains, and we'll demonstrate this here shortly with some of the examples on the psychrometric chart. There is absolute humidity, which is the measure of the maximum amount of water in grams per cubic volume of air. So it actually measures mass of water vapor in a sample of air. And then, of course, there's enthalpy, which we've discussed, which is the total energy present in the sample of air. So what is the psychrometric chart fundamentally? It is a reference chart. If you know any two air properties, dry bulb temperature and relative humidity, or dry bulb temperature, wet bulb temperature, or relative humidity and dew point, you can determine any other property of air on that psychrometric chart easily. And consequently, it can be used to evaluate HVAC processes through cooling and heating coils to see how air conditions change psychrometrically, and to evaluate the energy levels that need to be transferred within a building or from local zones. So, the psychrometric chart deconstructed. Well, let's look at the psychrometric chart. And that young gentleman on the right sort of reminded me when I saw that picture of me struggling with the psychrometric chart when I first entered into this industry. How do we make sense of it? And personally, I was always confused, though I'd attended a number of presentations that referenced only the chart, and I would just become visually lost in the lines. So I thought it might be a good idea to actually reevaluate the psychrometric chart by deconstructing it and then rebuilding it. And to do that, we're going to use a demanding environment that demonstrates an environment that needs to maintain within guidelines, codes and standard guidelines, given required air properties and conditions. We're going to look at a local healthcare provider's requirements for patient room and operating room designs. We'll take a patient room at 72 degrees at 40% relative humidity that needs to be maintained throughout the year. We're going to use a Phoenix design condition of 9776. People think of Phoenix, Arizona as our hot time of year when it's 115, approaching 120. In fact, we had 122 a few years ago. But anyway, we're going to use 9776 as our peak summer design condition. That actually has more total energy than a sample of air at 115 degrees at 10% RH. I know it's surprising, but it's true. We're going to take a sample of air from a healthcare facility. We're going to look at that sample of air at a condition of 72 degrees dry bulb, 40% relative humidity. And then we're going to take an outdoor air condition of 97 degrees, 76 wet bulb, or 39% relative humidity. To give you some orientation of the psychrometric chart, the x-axis is the dry bulb temperature line. The semi-parabolic lines spanning from lower left to upper right are the relative humidity lines ending at 100% RH at the topmost semi-parabolic line called the saturation curve. We're going to look at the y-axis, which gives dew point values. We're going to look at humidity ratio on its own independent vertical line parallel to the y-axis, and absolute humidity, again on the y-axis. And then see how enthalpy is represented by that long, straight, diagonal line to the upper left of the chart, and how we can actually read BTUs of energy along that enthalpy line. So let's look at this hospital patient room and let's see where the dry bulb lines are on the psychrometric chart. The dry bulb lines run left-leaning vertically from the x-axis that is given in 5-degree temperature increments along the x-axis. So if you wanted to identify the dry bulb lines, they are parallel to the lines represented here. That is your dry bulb temperature line. So if you have a room that's at 72 degrees, you draw a line parallel to the dry bulb lines up through the chart to identify its place on the chart. So let's look at our space condition for a hospital room at 72 degrees. We actually draw in the dry bulb line through the chart up through the saturation curve to give us an understanding of the full range of properties of air at that temperature. Well, let's look at relative humidity. Again, to repeat, relative humidity is a relation of the amount of moisture air can hold is a relationship of the amount of moisture present in a sample of air compared to what that sample of air can hold at a given temperature. So the relative humidity lines on the psychrometric chart are the semi-parabolic lines that span lower left to upper right in 10% increments from the x-axis up to 100% RH along the topmost curve called the saturation curve. So if we wanted to demonstrate what that air sample condition is on the psychrometric chart, we have to define a state point. A state point occurs where there's the intersection of two air property values on the chart. So you draw the dry bulb temperature line on the chart, and where that dry bulb temperature line intersects with the relative humidity line, you create a state point. And that state point can give you a value of how much energy is present in that sample of air. Wet bulb temperatures, which were frequently used, is still frequently used as the humidity reference in a sample of air in HVAC designs. Remember that the wet bulb temperature is measured based on a Sling Psychrometer's wick thermometer, and it determines the amount of moisture present in a sample of air based on the temperature generated from the evaporation of the water from the wetted wick. So where are the wet bulb lines on the psychrometric chart? The wet bulb reference values reside along the semi-parabolic saturation curve in 5-degree increments. And the wet bulb lines run diagonally from upper left to lower right and are all parallel. So if we want to determine the wet bulb temperature of a sample of air at 72 degrees, dry bulb 40% RH, we draw the dry bulb line and find out where it intersects the relative humidity line to create a state point. And then we draw a wet bulb line parallel to the wet bulb lines spanning from the saturation curve, and where that line intersects the saturation curve will give us the temperature value or the wet bulb temperature of that sample of air. And it works the other way as well. Historically, for HVAC equipment, we provide dry bulb and wet bulb conditions. Well, if you have dry bulb and wet bulb, you can determine where those two lines intersect, the relative humidity level of a sample of air. So it works both ways. Dew point lines. Dew point lines run parallel to the x-axis and 90 degrees to the y-axis. So if we need to determine the dew point of a sample of air, we take our patient room example of 72 degrees, 40% RH. We draw the dry bulb line, find out where it intersects the relative humidity line. We find our state point, and then we draw a horizontal line through the state point, and where that line intersects with the y-axis dew point reference line, or through the saturation curve, we can determine what the dew point value is. So a state point of 72 degrees, 40% RH has a dew point value at 46.4 degrees Fahrenheit. Well, that means that at that temperature, any water vapor in a sample of air that comes in contact with a surface at that temperature has insufficient energy to keep it in a gaseous state, and it will condense into a liquid. Consequently, it's called the dew point line. Well, there's an interesting relationship between wet bulb, dry bulb, and dew point. If we go back to our condition and we find our state point and draw the dew point line, notice that where the dew point line intersects the saturation curve, the wet bulb value that it intersects with is also along the dew point line. So if the dry bulb temperature and the wet bulb temperature are equal, it is also equal to the dew point temperature. Some psychrometric charts use that saturation curve as the dew point reference. I've seen psychrometric charts printed in both ways, with an independent line parallel to the y-axis on the right of the chart, and other charts referencing it at the intersection of the dry bulb, wet bulb point on the saturation curve. There's specific humidity as well that measures the amount of grains of moisture in a pound of air. Specific humidity lines also run parallel to the x-axis and are referenced as a value along a line parallel to the y-axis to the right of the psychrometric chart. So to determine the specific humidity of a sample of air, you draw your dry bulb line, find your state point, and you draw your specific humidity line through the horizontally through the state point line, and find out where on that that parallel line reference on the right of the chart intersects, and it's at that state point of 72, 40% RH. The specific humidity level is 48.68 grains of moisture per pound of dry air. So how do we determine energy and enthalpy? Well, again, we find our state point, and then we draw a line parallel to the wet bulb temperature lines, and where that line intersects the enthalpy line will give us the amount of energy in BTUs per pound of air in that sample of air. And that gives us a fixed amount of energy that we can assign with the properties of air at that state point condition. Well, the psychrometric chart has various different processes that it can be applied to. One is sensible heating, one is sensible cooling, one is just the process of humidification, where we add water vapor to a sample of air. There's dehumidification, there's evaporation, chemical dehumidification, heating humidification, and cooling dehumidification. So let's evaluate each of these and see the relationship the psychrometric chart reveals between all of these air properties. So if we look at a sample of air at 72 degrees, 40% RH, it has a dew point of 46.39 degrees and a specific humidity of 46.7 grains. Well, if we add sensible heat, we're adding sensible heat energy, and we raise the temperature to 81, look what happens to the relative humidity. It decreases to 30%. However, look at the grains. We still have 46.7 grains of moisture. That is why we say that specific humidity and dew point are absolute measurements of how much water content is in a sample of air regardless of its temperature. If that state point is raised to 95 degrees for sensible heating, again, look at the relative humidity value. It's now down to 19%, but our dew point and specific humidity values remain the same. So if we look at the energy gain, look at the energy in a sensible heating process that we would see in heating during our winter months. Temperature increases, relative humidity decreases, dew point remains constant. Enthalpy and total energy, however, increases. Let's look at sensible cooling, where we cool a sample of air from 72 degrees to 65 degrees. Look at how the relative humidity goes up, because at lower temperature, air cannot hold as much water vapor as air at warmer temperatures. There's not enough energy present in the sample of air to contain that extra water vapor. Look at how the dew point and the specific humidity values remain the same. As we reduce the actual sensible energy or dry bulb temperature even more, you can see how relative humidity can approach saturation at 46 degrees or dew point, while the grains of moisture remain constant for all of those conditions. So what happens to our total energy? Well, we lose energy. We lose thermal energy in that sample of air. Temperature decreases, relative humidity increases, dew point remains constant, enthalpy, total energy decreases. Let's look at the humidification process, where we add water vapor without increasing temperature. So we keep temperature at 72 degrees and we start adding water vapor. Look at how your relative humidity goes up, but also your dew point, grain, and grains of moisture, demonstrating that a sample of air now has increased moisture content. And without adding thermal energy, look how much enthalpy energy is added to a sample of air just by increasing the water content. Latent energy requires a lot of actual kW usage to remove, and is a substantial burden on the energy load and profile of buildings. Let's look at the dehumidification process. If we remove moisture from a sample of air without increasing or decreasing the temperature, relative humidity goes down, grains of moisture go down, and look at the amount of energy that is reduced when you actually reduce latent energy or moisture or water vapor from a sample of air. So it's substantial how much energy water vapor adds to a sample of air. So if you live in an environment in Georgia or the southeastern United States with high humidity levels, you still have a lot of energy in the sample of air, even though your temperatures are 90 degrees, 95 degrees versus maybe 110, 115 here in Phoenix. Let's look at the evaporation process, which is very interesting, because as water undergoes a phase change from liquid to vapor, what does water need in order to make that conversion from a fluid to a gas? It needs energy. So as water liquid evaporates, it absorbs thermal energy from the air, reducing temperature while increasing the relative humidity and the amount of grains in a sample of air. But what's interesting, because there's a reduction of thermal energy while there's an addition of latent energy to a sample of air, they offset each other, so there's no net energy gain through the process of evaporation. So you could just say you're robbing Peter to pay Paul in order to maintain the total energy levels within a sample of air. The same applies for chemical dehumidification or desiccant dehumidification, where we actually add energy to a sample of air by removing water vapor. And consequently, we notice that there's no net energy gain in that process of chemical desiccant dehumidification. What about heating humidification, where you might use a humidifier that uses gas or electric vaporization into steam? Again, you're adding heat while you're adding latent energy and moisture to a space. So you're actually adding the amount, you're increasing your grains of moisture as you see a net increase in the actual thermal energy to a sample of air, and consequently, you can calculate the measurable amount of energy increase through the heating humidification process. And then cooling dehumidification, we see by cooling a sample of air, dehumidifying the air that's crossing the cooling coil by bringing it to dew point, we can see how there's a substantial decrease in the amount of enthalpy or energy present in a sample of air. So let's look at a process. Let's look at an air handler of 10,000 CFM with 2,000 CFM of outside air, and we are returning 8,000 CFM. We're using an outdoor air design condition I referenced for our healthcare provider at 97 degrees dry bulb, 76 degrees wet bulb. We look at a return air condition of 75 degrees dry bulb, 50% RH. The first thing you need to do is calculate what the state point is of air in the mixed air condition by mixing the 2 and 8,000 CFM. Well, you can do that very easily, certainly through various apps that are available in the market. So determine the state point of your mixed air condition. In this case, it's 79 degrees dry bulb, 65 degrees wet bulb, or 58 degree dew point. The cooling coil leaving air temperature needs to be at 55 degrees in order to bring that sample of air to saturation and dew point, so there's not enough energy present in that sample of air to hold the moisture that is in that sample of air. Consequently, if we look at this process, we see a total amount of energy to be removed is required to allow air to achieve saturation. So we can not only remove thermal energy, but latent energy in that sample of air to maintain building temperature and humidity levels. Now, I want to show you an interesting factor as to why reheat is frowned upon in MEP designs these days, because of the amount of energy required to reheat a sample of air that has been conditioned to 55 degrees. And we see this common in healthcare facilities. So if we look at the sample of air, we look at the mixed air condition, we look at the saturation point the air is brought to maintain humidity levels in a building, and we look at the energy, right? 8 BTUs per pound of air that we discussed. Now, if you have to reheat that air back to 85 degrees, can you see you actually have to consume that much more mechanical energy or electrical energy to add the heat back into the space in order to reheat that air, to maintain those perimeter zones, perhaps in buildings like healthcare facilities that need to be heated while interior zones need to be cooled. So reheat really is, you're just doubling the energy consumption under those conditions. So let's look at the psychrometric chart and look at one common problem we see here in Phoenix, Arizona during our monsoon months. Let's look at the problem. Let's look at a healthcare facility lobby. We're going to look at ceiling diffusers condensing in the lobby during our monsoon months because hospital doors are opening and closing, and all that moisture from outdoors, all that latent energy is racing to go indoors where it's a drier environment. So how do we use psychrometrics to resolve a field way of evaluating a good solution to prevent condensation on diffusers. Well, when does condensation occur? Well, it's when the surface temperature or the temperature of the surface of something within a space is at space dew point. So if we look at the state point of a sample of air in a lobby that's conditioned to 75 degrees dry bulb, 50% RH, and we look at our psychrometric chart and draw our dew point line through the state point, we determine that the actual lobby dew point at 75 degrees, 50% RH is 55.12 degrees. Well, if you're conditioning your supply air off the cooling coil to 55 degrees, the chances are your diffuser is pretty close to 55 degrees. There's your condensation problem. So how do you use psychrometrics to determine a solution? What do we need to do that? Well, if you have a VAV box serving that lobby, which you usually do with reheat coils, then really just look at bumping using the reheat coil to bump the supply air temperature to 2 to 3 degrees above space dew point. Your condensation problem will go away because the surface temperature of the diffuser is above dew point. Condensation will not occur. So it's a very good way of determining the properties of air at a given condition to see what might be generating the condensation problem within a space. And by the way, this can happen as well within walls, perimeter walls of buildings. And our architects have to be very careful to make sure they have air barriers and vapor barriers properly located to prevent condensation from occurring inside walls where it can create havoc, generating mold, funguses, mildew, etc. So that brings us to an end of our presentation. So for a quick review, we've covered a lot of ground. We looked at the White House indoor air quality initiatives and how that is actually changing our industry. In order to evaluate how we respond appropriately, we've evaluated what heat transfer is. We provided terms and definitions for energy, both sensible and latent energy, total load, enthalpy, and looked at very briefly thermodynamics. We defined the properties of air as represented on the psychrometric chart: dry bulb, wet bulb, dew point, specific humidity. And then we deconstructed the psychrometric part in the hopes that it'll make it visually easier to identify the reference lines on the chart and how they can be used to evaluate other properties of air. One very important property I didn't go into, but I do cover it in my humidity presentation, and that is vapor pressure. So so to conclude, as we move into this era of high performance buildings, please realize that building thermal energy loads are decreasing. Airflow necessary to meet the thermal energy loads is decreasing. However, humidity is staying the same. So in order to maintain proper humidity levels in a building, make sure psychrometrics are applied appropriately so you can calculate how much latent energy needs to be removed to maintain buildings not only at constant temperatures, but also constant humidity levels. So very good. Thank you very much for your time. That is an end to today's presentation. Thank you for joining us today. Are there any questions?
Yes, it feels like we do have one question. It says, what do you typically look at in order to determine whether you should increase supply air versus lowering coil LATs?
The first thing is,
Oops. Dan, you're muted. I'm not sure why.
I don't know what happened. It's just I wasn't touching anything. It really has to do with really what is the capacity of the air handler and the chill water loop. Chances are it's going to be a local issue, so you would want to address the air handler serving that zone to see what added airflow capacity you might have to address it. Because if you have to do this chill water loop and lower chill water temperatures, you're now talking about perhaps a total building adjustment in chill water temperature. So the impact would be much broader. So I would say look at the fan first to see if you have the capacity to increase the airflow specifically to that zone. Maybe it's a VAV box, maximum set point adjustment, which begs the question, never lay out your VAV boxes to maximum airflow levels or size them accordingly. Make sure you have some buffer. But anyway, I would say the solution would look at the air side first before considering lowering the chill water temperature. Jen, you're on mute.
I don't see any others. I just see people saying, great job, Dan. Very impressive. They still learn something after after teaching psychrometrics for years. So unless anybody has anything else, I think we're good to go. So
All right,
since we're
well,
over time, so thank you all for your
thank you
patience.
for being here. And then in Psychrometrics Part 2, we actually used the chart to evaluate the psychrometric properties of air processes using medium pressure VAV air handlers, energy recovery units, both enthalpy and sensible only heat recovery. Then we look at the psychrometric process for air handlers serving displacement ventilation systems, and then 100% outside air systems. So please join us in October for Psychrometrics Part 2.